Last time, we defined the electric flux density D and derived Gauss's law, the first of Maxwell's equations. With symmetry, Gauss's law lets us find D in just a few lines of algebra. Today, we introduce the electric potential V, a scalar quantity that provides yet another way to find the electric field. We'll derive the EV relationship, which is the second Maxwell equation for static fields, and show why working with a scalar is often much easier than working with vectors. Suppose we move a point charge Q from point A to point B in an electric field E. The work done by an external agent against the field is W equals minus Q times the line integral of E dot dl from A to B. Dividing by Q gives the potential difference between A and B. VAB equals minus the integral of E dot dl from A to B. This quantity VAB is measured in volts, joules per coulomb. For a point charge Q at the origin, the E field is radial. Taking the reference at infinity, where V equals 0, the potential at distance r is V equals Q over 4 pi epsilon 0 r. This is a crucial result. Unlike the vector E, which has three components, V is a scalar, just one number at each point in space. And the potential difference VAB is independent of the path taken between A and B. The electrostatic field is conservative. Just as E obeys superposition, so does V. For n point charges Q1 through Qn at positions R1 through Rn, the potential at any point R is V equals the sum of Qk over 4 pi epsilon 0 times the magnitude of R minus Rk. Notice the enormous advantage. We're summing scalars, not vectors. No need to decompose into components and add separately. For continuous charge distributions, we replace the sum with an integral. For a line charge, V equals the integral of rho L dl over 4 pi epsilon 0 r. For a surface charge, V equals the integral of rho S ds over 4 pi epsilon 0 r. For a volume charge, V equals the integral of rho V dV over 4 pi epsilon 0 r. In each case, r is the distance from the source element to the field point. The reference point where V equals 0 is taken at infinity. We define the potential as V equals minus the integral of E dot dl. But from multivariable calculus, the total differential dV equals partial V partial x d minus x plus partial V partial y d minus y plus partial V partial z d minus z. Comparing these two expressions, we find E equals minus the gradient of V. In other words, E equals minus nabla V. This is tremendously useful. If we know V, a single scalar function, we can find all three components of E by taking partial derivatives. E points from higher potential to lower potential, and its magnitude is greatest where V changes most rapidly. Now, since the curl of any gradient is identically 0, we get nabla cross E equals 0. This is Maxwell's second equation for static fields. Its integral form is the closed line integral of E dot dl equals 0. Physically, no net work is done in moving a charge around any closed path in an electrostatic field. This confirms that the electrostatic field is conservative and irrotational. Let's see how the EV relationship simplifies calculations. Given the potential V equals 10 over r squared times sine theta cosine phi in spherical coordinates, find E and calculate the work done in moving a charge. First, E equals minus nabla V. In spherical coordinates, the gradient has three terms: partial with respect to r, 1 over r partial with respect to theta, and 1 over r sine theta partial with respect to phi. Taking each partial derivative, we get ER equals 20 over r cubed sine theta cosine phi, E theta equals minus 10 over r cubed cosine theta cosine phi, and E phi equals 10 over r cubed sine phi. Now for the work. Moving a 10 microcoulomb charge from point A at r equals 1, theta equals 30 degrees, phi equals 120 degrees, to point B at r equals 4, theta equals 90 degrees, phi equals 60 degrees. Method 2 is much easier. W equals Q times VAB, which is Q times VB minus VA. Just plug in the coordinates. V at A is minus 5, V at B is 10 over 32. So W equals 10 microcoulombs times the difference, giving 28.125 microjoules. No line integrals needed. That's the power of working with the scalar potential. Let's recap today's key ideas. VAB equals minus the integral of E dot dl. The potential difference is path independent. For a point charge, V equals Q over 4 pi epsilon 0 r. Potential obeys superposition, some scalars, not vectors. E equals minus nabla V. Find the vector field from a scalar function. This is Maxwell's second static equation in differential form. The integral form is the closed line integral of E dot dl equals 0. Next time, we'll explore the electric dipole and energy stored in electrostatic fields.